Okay, thank you everyone for joining in, and a very warm welcome to the first talk for data conversations. We are very happy to inaugurate, the technical seminar series with a very eminent speaker, Professor Masashi Sugiyama. Professor Masashi, he has completed his PhD in computer science from the Tokyo Institute of Technology in 2001, and he's been a professor at the University of Tokyo since 2014. And concurrently, he's also the director of the RIKEN Center of Advanced Intelligence Project since 2016. He serves as a program co-chair for many conferences, including NeurIPS, AI Stats, ACML, etc. And he's also co-authored a couple of books in the areas of in machine learning, density ratio estimation, and so on, right? So today he's going to be talking to us about improving robustness in data-centric machine learning. And, we're looking forward to a very exciting talk. So thank you, Professor Masashi, for accepting our invite, and thank you for taking out time for giving us a talk here. So once again, I warmly invite you to this session.
Yeah, thank you, Hima, for the nice introduction. And good morning, everybody. I'm Masashi Sugiyama from RIKEN and the University of Tokyo. So it's my great honor to be the first speaker of this data conversation seminar series. So hope that we can have nice discussion at the end of the talk. So okay, before starting, let me briefly introduce myself. So I'm currently director of RIKEN AIP. Actually, I have a few more slides about RIKEN. I will talk about it later in more detail. But RIKEN is a national research center in Japan. So there we hire like postdoc researchers basically. So then at the universities, I'm professor at the University of Tokyo. So I have graduate students there. We are working together. In addition, so we need more researchers and engineers. So I try to do some consulting jobs at several local startups in Tokyo. And as I introduced, so I'm interested in machine learning theory and algorithm. And usually I spend about 10 years on one topic and publish one book. So now I have 6 books here. So that means I'm already over 60 years old. But actually, I'm slightly younger than that, because some projects are overlap. But I have been interested in like machine learning in non-stationarity adaptation or reinforcement learning and variational Bayesian learning, and more recently, machine learning from weak supervision. So these are my basic research. Then I'm also, in principle, interested in applications of machine learning. But this is way beyond what I can do by myself. So I always try to find nice partners in industry or some other research centers and try to ask them to use our machine learning method. So that's the reality. And so far, I was so lucky to have nice partners, and we could have several nice applications in these domains. Then, as I introduced, I was the program chair for NeurIPS, AI Stats, and ASML. And even last month, December 2022, so I was in Hyderabad and I joined ASML 2022, and it was an exciting conference there. So let me briefly talk about my current affiliation, RIKEN. So RIKEN is a national research center in Japan, and its name in Japanese is actually like this, 6 letters. The first 3 letters are pronounced as Rikagaku, and the last 3 letters were pronounced as Kenkyusho. And altogether, so these 6 letters mean the Physics and Chemistry Research Institute. And many years ago, RIKEN was, in English, RIKEN was set as like a research institute for physics and chemistry or something like that. But okay, 6 letters are too long for Japanese. So we prefer to shorten it into 2 letters. Pick this first letter and pick this first letter, and 2 letters like this. And this is pronounced as RIKEN in Japanese. Then at some point, so maybe the president or some executive directors decided to use this Japanese acronym, RIKEN, as an official international name. So that means RIKEN is no longer an acronym, but this is the official name of our research center. Please remember RIKEN. So RIKEN actually started the AI project about 7 years ago. So actually, Ministry of Education started a project called Advanced Intelligence Project in 2016. And RIKEN AIP is a center of pursuing this research project. And now we have about 130 employed researchers, and more than 1/3 is international, and about 1/4 is female. So I think our center is reasonably diverse. Then we have about 200 visiting researchers from industry and universities. And also we have about 100 domestic students in Japan. Then before the COVID pandemic, we actually invited 140 international interns over the world. But in the last couple of years, we stopped this program because of the travel restrictions. But from this year, we gradually restarted this internship program. So hopefully we can also invite students from India to our center for interns. And at RIKEN AIP, so we have 5 research missions. The first mission is to develop new AI technology. So this is actually the main topic of my talk today. So we are doing basic research on machine learning, optimization theory, and some applied math projects. And the second challenge is to accelerate scientific research. So in Japan, research on like cancer, material science, genomics, so these are quite popular. So we have partners inside Japan and try to like accelerate their scientific research based on AI and machine learning. Then the third challenge is to solve socially critical problems in Japan. So in Japan, we suffer a lot of natural disasters like tsunami and typhoon and heavy rain. So we try to predict those disasters. Or elderly healthcare is another quite urgent challenge in Japan. So we have a large number of elderly people in Japan. It's a like super aged society now. So we need to really support them. And also education is another important challenge for us now. And the fourth topic is the study of ethical, legal, and social issues of AI. The first 3 topics are more on like science and technology. But the fourth one is more like social scientific things. So we are interested in also like ethical guidelines of AI, or personal data management, and things like that. And finally, human resource development. I think in India, quite a lot of students are working in computer science and doing machine learning and AI research. So this is great. But unfortunately, in Japan, still the number of like AI researchers and engineers are quite limited. So we need to really grow those engineers and researchers by working together with us. So our center is actually located really in the center of Tokyo. So our office is located in this building, actually on the 15th floor somewhere here. So this is actually 10 minutes walk from the central Tokyo station. Then we have a nice open discussion room like this. And also several teams are distributed across the entire Japan, but some teams are from different universities. And we decided to locate their labs in each university like this. So it's a quite diverse center. And here's some highlight of our recent research, like towards developing new AI technology. So we first worked on theory of deep learning. So we tried to show that deep learning is really better than shallow learning mathematically. And we could successfully prove that in some cases. And also we are interested in developing new methods of machine learning, like weakly supervised learning, noise robust learning, causal inference. So I will talk about some of the topics here today. Then the second part, accelerating scientific research. So we are working on medical science projects like prostate and pancreatic cancer detection, or ALS, early diagnosis, and things like that. Well, material science. Actually, this is an interesting project. So we use basically natural language processing technology to scan the papers published in the field of material science and try to create a database automatically from the papers. Then the last topic, data-driven science. So this is also a big issue because once we obtain some empirical results, experimental results, then we need to do hypothesis testing. But in this data-driven science era, so hypothesis was generated after looking at the data. Then actually the standard hypothetical testing methods are actually biased. So we need to somehow remove the bias of the testing. So this topic is paradigm is called selective inference. And we are working on developing some methodologies of selective inference nowadays. Then the third one, solving socially critical problems. So we are interested in natural disasters. And Fugaku is one of the fastest supercomputers over the world. And it is actually located in RIKEN. So we use this Fugaku to simulate earthquakes in the area of Japan. And also we are analyzing remote sensing images taken by some satellite. We have kind of online and real-time analysis nowadays. Then for elderly healthcare topics, we are working on developing a chat robot guided cognitive function system, cognitive function improvement system. So we basically prepare a small robot, and this is like the chairperson of the chat among elderly people. Then so this robot guides the discussion. Then actually in the long run, so the speed of cognitive function decline can be slowed down by this kind of chat sessions. And finally, education. So we are interested in utilizing the natural language processing technology to evaluate the written essays automatically. And also we try to support essay writing based on the NLP technologies. And finally, the study of AI ethical, legal, and social issues. And in the beginning of the project, we worked on setting up the AI ethical guidelines, like together with Japanese Society for Artificial Intelligence, Ministry of International Affairs and Communication, and also the Cabinet Office of Japan. So we contributed some to the AI ethical guidelines. And later, these were proposed in IEEE and G20 and OECD. Then we are also interested in personal data management. And maybe in some companies, so in some countries, big companies are having personal data and they use them for improving their service. In another country, maybe the government holds the data and they keep the data secret. But in AIP, so we try to propose a different system called individual-based accessibility control system. So basically, each individual encrypt their personal data and put it on cloud service like Google Drive or Dropbox. Then, so each individual actually control the access from like the third party or local government or company. So by that, so we can personally really control the accessibility by ourselves. So we have a nice system already in Japan, and this is tested in some education program now. And finally, AI security and reliability. So maybe many people know that the current deep learning system is quite vulnerable to adversarial attack. So developing a defense strategy is one of the urgent challenges nowadays. And also we found that fairness issues is quite important in this security context. So actually we can show that fairness can be even fake. So this is a kind of interesting finding, but we need to somehow avoid this problem. So we try to guarantee that fairness is really guaranteed by some system. So this is our another challenge now. Okay, these are something so we are doing at RIKEN AIP. So then this second section is the main part of my talk today. So I will talk about robust machine learning in the data-centric context. So the goal of our research, my team, is to develop novel machine learning theories and algorithms that enable reliable learning from limited information. To achieve this goal, we are working on several interesting topics, and some are listed here. The first one is learning from insufficient information, because often we don't really have enough training data to train our predictor. And often maybe our data only contains weak information, weak supervision. Still, we want to do supervised learning. So this is the first challenge here, weakly supervised learning. And the second issue is data bias. Maybe sometimes our training data is biased, maybe due to some changing environments, or maybe due to some privacy concern. We are not allowed to access the data as we want. Then the data could be biased. But we want to train our predictor in an unbiased way. So this is the topic of transfer learning or domain adaptation. So I will talk about this later. Then the third one is label noise. So now we have big data, and often labels are collected like through some human or some crowdsourcing, for example. Then we have a lot of human errors. And also if we collect label information from sensors, then sensor intrinsically contains some errors, some noise. We want to overcome this label noise. And finally, adversarial attack. So we want to cope with adversarial noise and adversarial distribution shift and things like that. So today, basically, I briefly talk about the first three topics. So let me start from the first one called weakly supervised learning. So nowadays, machine learning from big label data is quite successful in many application domains like speech recognition, image understanding, language translation, and online advertisement, etc. So let's consider the simplest problem. So we have a binary classification problem like this. Then we have positive data, negative data, and we want to learn the boundary between two classes. And we know that estimation error of this boundary decreases in the order of 1 over square root of n, where n is the number of label samples. So 1 over square root of n is a function like this. So this means if we can collect 4 times more samples, then the estimation error is half. If we have 100 more samples, then the estimation error is 1/10. So this is a general result. However, there are various applications where big label data is not really available. Like we are working on some medical project or natural disaster project. So in this project, collecting label data is extremely difficult and sometimes impossible. Or in the applications of robot control or brain signal analysis, the labeling is extremely expensive. So somehow we want to avoid so big label data issue. Then one of the naive approach is to use unsupervised classification instead. So this is a kind of extreme case. So we don't use any single label. So all data points are just unlabeled in this way. Then essentially what we can do is clustering. So given like these data points, maybe by clustering, we obtain a boundary like this. Then, so okay, if one cluster, so let's say top left one corresponds to one class, like all red, and bottom right cluster corresponds to all blue, then so this clustering method works perfectly fine. But in practice, maybe each cluster may contain many different class labels, so blue and red here. Then there's no guarantee for prediction. Then a slightly improved approach is semi-supervised classification. So in addition to a large number of unlabeled data, we use a small amount of labeled data. Like in this example, so in addition to unlabeled data, we have one positive point here and one negative point here. Then the basic idea of semi-supervised classification, traditional method, is to propagate these given labels over clusters, along clusters. Like this blue point is propagated over this cluster in this way, and this red point is propagated over the cluster in this way. By that, we can somehow color each cluster in a nice way. And again, once the clustering is really working well for classification, then this semi-supervised method works really well. But in reality, maybe each cluster contains both red and blue. Then, so this semi-supervised classification methods do not work well in practice. So to cope with labeling cost, so we can think of several different approaches. Maybe we can improve the data collection process itself. For example, by using crowdsourcing, but then data is quite noisy. Or we may use a simulator to generate pseudo data, like in the case of physics experiments, or chemistry, process, or robot control. So this is possible for some applications, but they are not, such a simulator is not always available in data analysis. Or we always use domain knowledge to improve the performance. Maybe this is done everywhere when we work on real applications. And finally, we may use cheap data, but it only contains weak data, weak information. So this is our focus today. So the typical example of cheap but weak data is unlabeled data. But we can generalize the scenario a bit more. I will talk about this in the next few slides. Then the summary so far is like this. So I took the classification accuracy on the horizontal axis, low and high. Then the labeling cost, so high and low on the vertical axis. Then the supervised classification is located somewhere here. So it achieves the highest classification accuracy but the labeling cost is highest because all data needs to be labeled. Then unsupervised classification, so basically the labeling cost is 0, so it's the lowest. But the classification accuracy is not reliable, not guaranteed. So it is located on the bottom left corner here. Then semi-supervised classification. So classification labeling cost is still low, but still the classification accuracy is not that much guaranteed in practice. So it is still located on the left-hand side of the illustration. So our goal is to explore this bottom right corner. So we are interested in high accuracy and low cost learning. So this is weakly supervised learning. And we have developed several interesting methods so far. And this is something I want to introduce in the next few slides. Okay, so one of the typical examples of weakly supervised learning is called positive-unlabeled classification. So I am still considering the binary classification problem where so we want to classify blue points, blue positive points, and red negative points. But in this PU classification, positive-unlabeled classification, we only have positive data and unlabeled data, black ones, but no negative data, so no red points. So given blue and black, so we want to separate. We want to separate blue and red. So this is the problem here. So given blue and black, we want to separate blue and red and obtain this kind of decision boundary. So this is the goal of PU classification. And this PU classification scenario is observable in many applications actually. And in textbook example, so advertisement click prediction is the typical one. So clicked advertisement is a positive data because the user likes that advertisement. But unclicked advertisement is actually unlabeled because we are not sure whether the user dislikes it or the user likes it, but he or she didn't have time to click it. So at this point, we don't know whether the unclicked link is positive or negative. So this is still unlabeled. So in this scenario, we only have positive data and unlabeled data naturally, but we want to classify positives and negatives. So this is PU classification. And let me spend one page to explain the derivation of the method. So maybe you can skip it if you are not interested. So we are given positive data set from positive density, and then unlabeled data set from marginal distribution. Then, so as usual, so we define the classification risk. So here's a loss function L, and this is expected over the entire data density. Then this classification risk is decomposed into the risk for positive data and the risk for negative data. And in the standard case of supervised learning, we have positive data and negative data. Then these expectation over positive data and the expectation over negative data can be naturally approximated from given data. But in the current PU classification scenario, we only have positive data and unlabeled data. So the first term is fine. We can use our positive data. The second term cannot be directly approximated because we don't have negative data. So this is the technical challenge here. So by the way, we have pi here and 1 minus pi here. The pi is the positive class prior. And today, for simplicity, I assume this pi is known. But in practice, we need to also estimate pi from data, from PU data. And already there's a series of papers working on estimating pi from PU data. And I must admit, so this is still a challenging problem, but there are several practical methods. So in practice, we can use that kind of method to estimate pi and plug estimated pi into these parts. Then we can simply solve the problem. So for now, so let's assume pi is known. Then so let's come back to the second term. So this is unknown. So we estimate it only from positive and unlabeled data by this trick. So we know that Px, so this is the unlabeled data density. The Px is a mixture of P of the positive density and negative density. And the mixing proportion is pi and 1 minus pi. Then, so this part actually can be approximated, can be replaced with Px minus P of x given y equals +1. So I just plug this relation into here. Then the second term can be expressed in this way. And the first term is actually the expectation over unlabeled data. And this term is expectation over the positive data. Then we can approximate them by PU samples. Then in the end, we have this objective function. So this can be computed only from positive data and unlabeled data. And F can be any classifier, maybe a neural network. And we minimize this R hat PU by stochastic gradient descent. So this is our solution. Then, so theoretically, we can show that, okay, this achieves the optimal convergence rate. So 1 over square root of NP plus 1 over square root of NU. So this is a simple method, but this is already mathematically optimal. Then one more nice extension of that method is, now we can solve PU classification problem. Then we can also solve the semi-supervised classification problem in a nicer way. So recall that the semi-supervised classification contains positive data, negative data, and unlabeled data like this. So our approach is to decompose this PNU problem into PU, PN, and NU. Then this PU problem can be solved by the method I showed in the previous page. Then NU problem can also be solved in the same way, because it is just a flipped version of PU problem. And the last one, PN classification problem. So this is the standard supervised learning problem, so we can also solve it. Then our solution is quite simple. So we prepare 3 different learning objective functions and just linearly combine them and minimize them all together. So this is our solution. So it's quite straightforward. But we can show that even without any cluster assumptions, so the method by minimizing these 3 criteria at the same time, so we can actually achieve the statistical consistency like this. So this means that we can really solve the semi-supervised classification problem in an optimal way. So in particular, we have 1 over square root of NU term here. NU is the number of unlabeled data. So this means that if you have more unlabeled data, then the prediction performance is improved without having strong assumptions like clusters. So this is a quite interesting and strong result. And finally, so this approach can be extended to more interesting scenarios. So from PU classification to positive confidence classification, or classification from 2 unlabeled data sets, or classification from only similar dissimilar information like this. So all of these methods, these problems can be solved essentially in the same way in the unified framework. And so all are loss correction based and all are statistically consistent. So we can achieve this optimal convergence rate. And the formulation is actually general enough. So it can accept any loss function, any classifier, and any optimizers. So it's a quite flexible framework. Then, so we now extend our discussion to multi-class classification, because labeling pattern is even more painful in multi-class classification. Like in image classification problems, nowadays we have thousands of classes. Then labeling a sample is actually extremely time-consuming. We have a list of thousands of labels. Then we need to choose the right one. So labeling is extremely time-consuming and painful. So to mitigate this problem, so we considered the following multi-class weak labels. First one is called complementary labels. The ordinary class label specifies class that a pattern belongs to. Like this sample belongs to class 1, or this sample belongs to class 3, or this image contains dog or something like that. But complementary label is its complementary version. So it specifies a class that a pattern does not belong to. Like this sample does not belong to class 3, or this sample does not belong to class 1, or this image does not contain cat or something like that. It's a complementary label, and it's actually much cheaper to obtain. But we can show that only from complementary labels, we can still train the classifier in an optimal way. Then this notion of complementary label can be generalized to partial labels. The partial label is a partial label specifies a subset of classes that contain the correct one. Like this sample belongs to either class 1 or 2. but this image contains either dog or cat, something like that. So it's an ambiguous label. But we can again show that only from partial labels, ambiguous information, we can still train the classifier in an optimal way. And finally, single class confidence. So in multi-class classification, suppose we can observe samples only from one class, let's say class 1. But if this class 1 samples are equipped with full confidence, like this sample belongs to class 1 with 60%, class 2 with 30%, and class 3 with 10% or something like that, then only from one class data, we can still train a multi-class classifier in an optimal way. So this is called learning from single class confidence. So again, so all of these weak labels can be handled in a unified framework. Systematic loss correction achieves the optimal convergence rate in this way. So altogether, so we explored this region, so lower labeling cost, but higher classification accuracy. And we developed an empirical risk minimization framework for weakly supervised learning. And this is quite general, and all weakly supervised labels can be handled in a unified way. So last summer, we published a book on this project. So we have been working on this project for about 10 years, and finally, so we could publish a book. So if you are interested in more details of machine learning from weak supervision, it's great that if you could take a look at this book. Okay, that was about weakly supervised learning. But then latter two parts are quite short. So let me quickly go through the remaining two topics. So the second topic is transfer learning. So training and test data often have different distributions because of changing environments or some privacy concerns based on sample selection bias. Like we may have training data only from the left-hand side, but the test data appears on the right-hand side or something like this. So in this kind of scenario, so it's often called transfer learning or domain adaptation. So we try to train a test domain predictor using the training data from different domains. Like we want to predict these test points only from blue training points, something like this. I have been working on actually this topic for about 20 years already. And in 2006, so more than 15 years ago, actually we organized a workshop at NIPS. There was a workshop on learning when test and training inputs have different distributions. And after that, we had an exit volume of this workshop 3 years later. But interestingly, this transfer learning and domain adaptation topic is nowadays very hot. And even NURIPS last year, so we actually organized a workshop there, and we had more than 100 submissions to our workshops. So this topic is back, and I'm quite interested nowadays. So about 10 years ago, the classical approach for transfer learning was something like this. So it's basically two-step adaptation. So in the first step, so so-called importance weight is estimated. The importance weight is W here, and it is actually defined as the ratio of two densities, like P test density over P training density. So we want to estimate this ratio. So this is the first step. Then once this ratio is estimated, then we use this as a weight for the loss function and train a predictor based on this estimated weight. So this is the second step. Once the importance weight is estimated quite accurately, then we can actually obtain a quite nice solution. So that adapts to the test domain from training data. But in this process, in this two-step process, the estimation error in the first step is not taken into account in the second step. So maybe we can solve the first problem quite accurately, but still not perfect. Maybe W hat contains some small error. But this small error can be actually magnified in the second step because we didn't care the second step when we performed the first step. So this is actually an essential problem. And we want to somehow overcome this limitation by integrating these two steps. So this is the challenge. And so we are aware of this challenge already 10 years ago, but at that point, we didn't have a solution to the question. But recently, we had two nice methods to overcome this problem. So let me briefly introduce these two approaches. The first method is called joint weight predictor optimization. So in this paper, so we consider the problem called covariate shift. In covariate shift, only the input distribution, P of X changes, but the conditional distribution, P of Y given X, does not change. So this is called covariate shift. And we assume that we are given labeled training data from the training density and unlabeled test data from test density. So this is often called unsupervised transfer learning. Then, so our solution is to minimize the risk upper bound jointly with respect to the weight W and predictor F. So I didn't really prepare detailed the equations here, but for the true risk, we obtain a certain upper bound. And this upper bound depends both on W and F. And we minimize this empirical version of this upper bound with respect to both F and W. Then actually we can show that so it achieves a consistent solution. So our solution has this kind of guarantee. So this is actually quite strong. And also we found that our upper bound is actually the sum of two learning objectives here. So this is actually quite interesting because previously we minimized the first criterion, then after that we minimized the second criterion. But now our upper bound is the sum of these two. We try to minimize both at the same time. So we can really minimize the upper bound. So this means the previous two-step adaptation is really suboptimal because two terms are minimized one by one. But now we can minimize both of them at the same time with guarantee. So this is a very nice result. Then the second method is called dynamic importance weighting. So in this paper, we consider general changing distribution. So joint distribution changes between the training phase and testing phase. So it's a quite general setting. And we assume that we are given a reasonable number of labeled training data from training domain. Then, so we have a small number of labeled test data from test domain. Then, so we train a neural network in a mini batch manner. And then for each mini batch, so we select small mini batch from these two data sets. So we estimate the importance weight by matching the loss functions by kernel mean matching. So more specifically, so we have a small number of labeled test points, so we can compute the average loss for the test data. If this is unreliable because we only have a small number of samples, then left-hand side, so we have labeled training data. So this has a reasonable size, but the distributions are different, so they are biased. So we have an importance weight again here, Ri. And this Ri is learned by kernel mean matching. Then, so we must say that maybe this is not really accurate because the right-hand side is quite unreliable because the mini batch size is quite small. But this is fine because it's just a one step of stochastic gradient descent. So maybe our gradient is still noisy, but we can somehow cope with the distribution shift by matching the distribution in this way. So this is an extremely simple solution, but it's actually highly powerful because basically we don't really need any assumptions on the changing distributions. Because almost all previous works on transfer learning or domain adaptation required some kind of constraint on the change between the training distribution and testing distribution. But this is free from such a restrictive assumption. So it's a simple but quite powerful method. Okay, so this is a summary of the transfer learning part. So we argue that in transfer learning with importance weighting, simultaneously performing importance estimation and predictor training is quite important and promising. But what should we do if the training and testing distributions look quite different? So one possible solution is to transfer data generation mechanism. We had one paper on that. So given multiple training data set, and we assume that some data generation mechanism are behind the actually common. Then we apply a kind of independent component analysis to decompose our training data into independent factors, and then so estimate the mechanism in this way. then try to transfer this mechanism in the target domain. Then we can make nice prediction here. And more recently, we are interested in working on the continuous distribution change. Like in our discussion so far, we only had training distribution and one testing distribution. But in reality, maybe the testing distribution is also changing over time. So we want to take into account this multi-step distribution change. And luckily, we had one paper in last new RIPS, and this is one of the first methods to cope with continuous distribution change. But we had a bit strong assumption that the change of distribution is only class priors. So now we are extending this method to be cope with more general distribution shift. And hopefully we can have a nice unified framework of continuous distribution change. Okay, then last part, so noise robust learning. So this part is even shorter. So supervised classification with clean labels is something like this. We have clean labels like this, and we obtain decision boundaries. So this is a kind of standard setup, and we just try to minimize the training error or likelihood, maximize the likelihood. Then our solution is statistically consistent, and it works well in practice. But in real world, maybe data is quite noisy. Labels are quite noisy like this. But often, okay, we have a large number of noisy labels. So let's just minimize the training error. So this is what people are doing in reality. But we can actually easily show that training error minimization is actually not really consistent anymore. This means that even if we have infinitely many noisy labels, still like our solution is not optimal. So that means, so we need a explicit way to get rid of the label noise. Otherwise, our solution is not good. So to cope with label noise, maybe there are several different approaches, classical approaches. So one is to remove outliers in an unsupervised way. Like given data points, we try to identify outliers like this and get rid of them. So this is nice, but maybe unsupervised outlier removal is substantially more difficult than like supervised classification. So maybe in reality, this approach is not so reliable. Then people use robust loss functions. In the case of regression, so we use squared loss in a standard way, but to make it robust, people use so-called Huber loss. The increase is not quadratic, but only linear. By that, we can suppress the influence of large noise. And this can be extended to classification scenarios. Like instead of the squared hinge loss, you may use the Huber loss like this, or even rump loss like this. So this is extremely robust. But still, the effectiveness of this robust loss approach is limited in classification. And finally, some more popular approach would be regularization. So we try to smooth the solution, and by that, we want to suppress the overfitting problems like this. So given noisy data, so the original solution is quite overfitted like this. But once we apply regularization, we obtain a smooth boundary like this. And this is good, but again, so if we have very strong label noise, like if this point is flipped into red, or if this point is flipped into blue, then we need to really smooth the solution very strongly. Then in the end, our solution is actually underfitted. So there's clear trade-off between noise suppression and underfitting. So that means regularization is also not so promising in the classification scenario. So we need new approaches. And one of the important concepts to cope with label noise is so-called noise transition matrix, T. Basically, T represents the probability of flipping a clean label to a noisy label. Like in the 3-class case, we have a 3x3 matrix, and 1, 0, 0 means so class 1 label is always class 1 with probability 1, but 0.1, 0.8, 0.1. So this means class 2 label is 80% correct, but with 1%, with 10%, it becomes class 1 or class 3. And finally, so 0.5, 0.50. So this is really a bad case. The class 3 label is never true. So it is always either class 1 or class 2 with 50%. So the noise transition matrix T describes this kind of noise label flipping probability. Then Patrini et al. Showed a very nice solution to this problem. So it's called loss correction approach. So T is basically a noise process. Then T inverse is a kind of denoising process, and they applied T inverse to the loss function. Then we can somehow eliminate the influence of noise in a nice way. Or similarly, we can adjust the classifier's output by applying T transpose to simulate noise. Then we can again remove the bias of estimation brought by noisy labels. But this method works well. These approaches work well only when the noise transition matrix T is given. But in practice, we need to estimate T from noisy data. So this is another big challenge. And today, I don't really go into the detail, but we have been working on this topic for like 4 or 5 years now. And we had a series of estimation methods of T. And now, in the last paper, we had a kind of reasonable solution to estimate T only from noisy data. So now, by combining Patrini's approach with our estimation of T, we can really solve a label noise problem in a nice way. Then beyond class conditional noise. So in the previous page, the assumption was that the label noise does not depend on instances. This means that, in this, like this figure, label noise appears here and there uniformly. But in practice, maybe noisy labels appear near the boundary, because these points are quite difficult to label. So it's easy to make a lot of mistakes around the boundaries. So this kind of noise is called instance-dependent noise. So instance-dependent noise basically is a function. So noise transition matrix T is a function of X. So this is an extremely challenging problem because even without X, estimation of T was difficult. But now it's a function of X, so it is almost impossible. So far, we only provided a few heuristic solutions. So based on parts-based estimation or use of additional confidence scores or manifold regularization under some assumption. But we still need more like unified framework to handle this instance-dependent noise. Then finally, one more slide on the method of co-teaching. So this is a completely different line of research. So this co-teaching method is based on the memorization properties of neural networks. Let's consider data sets like this. Then if we use stochastic gradient descent to optimize the neural network parameter, then we can immediately obtain this kind of solution. So this means clean data points are fitted quite faster. But if we want to really fit these noisy labels, noisy data points, then we need more stochastic gradient iterations to like change our boundary in this way. It takes more time to obtain this solution. So this implies that RE stopping is a nice solution to overcome label noise. And this is true. But in reality, RE stopping is actually quite difficult to implement in the proper way. So then our idea of co-teaching comes. In the co-teaching method, we prepare 2 neural networks. Let's call them A and B. So they are just duplicated, the same network. And we train A and B independently. Then, when we train A, we use a mini batch training. So we select a mini batch of data and perform stochastic gradient descent. Then we select some small loss data that are fitted faster. And those small loss data are regarded as clean data, noiseless data. And we select them and choose them to network B. And B does the same thing. B selects small loss data independently and select them and choose them to teach them to A. And this is repeated until convergence. Then we can in the end obtain a solution that is not affected by noisy labels. So that's the basic idea of co-teaching. And later we found that teaching only disagreed data can further improve the robustness. And also we found that even large loss data is actually useful. So this is actually a quite interesting idea because in the beginning, we tried to get rid of noisy data by throwing away large loss data. But later we found that these large loss data also contain useful information, because if we fit these large loss data by stochastic gradient descent, then with high probability, our solution is trapped by one of the poor local optimum, overfitted solution. So in a sense, finding a large loss data is a kind of nice precaution. So if we follow the current gradient, then there's a possibility that our solution is trapped by a poor local optimum. Then one possibility is to perform gradient ascent for these large loss data. So this basically means gradient ascent back along the gradient. So we try to get away from the potential poor local optimum. Then after going back, we select another mini batch of data, then perform the next gradient, the stochastic gradient descent. By that, we can successfully avoid the poor local optimum. So basically, there's no theory for that. It's just heuristic and empirical findings. But this method is extremely robust. So even when the 50% of labels are randomly flipped, still our solution is improved in this way. So this is an extremely robust approach, and maybe in the future we need more theoretical analysis for this method. Okay, thank you. This is the last slide. So I talked about reliable machine learning today. So reliability for expectable situations were basically the target today. So we tried to model the corruption process explicitly, like label noise is generated in this way and in that way, and try to correct the solution. But in this process, of course, there might be a modeling error. So our corruption process model is not really correct. So how to handle the modeling error is still an important challenge to explore. Then another different approach would be to consider reliability for unexpected situations. Like for example, so the simplest approach is to consider the worst case robustness. So we consider the worst case scenario. Still, we try to train our classifier to cope with this worst case scenario. It's a minimax solution. But in reality, such a minimax solution is extremely conservative. Like when we train a robot, then the minimax solution is not to move at all. Because once the robot moves, then there's a possibility that it is broken. So then the safest choice is to stay there and do nothing. Such a conservative solution is not useful in practice. So we want to make it less conservative. So this is a challenge now. Then another possibility is to include human support. So we want to ask humans to check samples. Yeah.
Hey, sorry to interrupt. We have the last 3 minutes left, and we want to end on time.
Okay. So
and we have 2 questions. Okay.
Yeah.
Yes.
Okay. Thank you. Then I stop it.
Okay, thank you. I do see there are 2 questions in the chat, so I will read them out. There's a question from Piyush Singhal. Does co-teaching reduce the number of epochs, and what are the other benefits? And he's referring to the work on slide 29.
Yeah, thank you very much. Actually, co-teaching increases the number of epochs. So we want to actually increase the number of epochs so that the solution does not overfit the noisy data. So this is a kind of weakness of the method. It takes more time to train the model, but it becomes extremely robust. So it's a kind of trade-off between like computational efficiency and noise robustness. Actually, going beyond this trade-off would be an important challenge. Thank you very much for the nice comment.
There's one more question from the same person. What is meant by propagating the label through clustering on slide 10?
What is the question?
What is meant by propagating the label through clustering?
Member?
Propagate labels along clusters. On the slide, there's a point around semi-supervised classification. Point number 2, propagate labels along the clusters.
Yeah.
So the question is, what is meant by that point? If you could expand on that point a little bit more.
This is just a heuristic, because once one cluster corresponds to one class, then so that's just propagating labels across the entire cluster will give a good solution. In particular, for some simple data set like USPS or maybe some CIFAR data set, then so this kind of label propagation works quite well. But in some other applications, maybe there's no clear cluster structure. Then this kind of semi-supervised classification methods do not work well. So we want to somehow avoid making an assumption that one cluster corresponds to one class. So this is actually a quite important challenge in semi-supervised classification. And our solution is one of the methods that can cope with this problem.
Thank you, Professor. We do have one more question. We're also at the end of time, so it's a multi-part question. So we'll just take the first part of it, and then for the remaining parts, we will try to address it offline via email. So the question is, how does the proposed solution with PU plus PN plus NU estimation in a binary case translate to the multi-class setting?
Yeah, thank you very much. That's a very nice question. So if it's a multi-class let's say C-class classification, then if we have labels from C-1 classes, then still we can apply this technique in a naive way. But if you have like 2 or more missing classes, then there's no way to distinguish classes in those unobserved classes. So to cope with that problem, we need some additional heuristic techniques to cluster data.
Okay. Thank you, Professor Masashi. I think there's the follow-up questions for the same part, but we are at the top of the hour. So we'll probably, I think, send them to you offline and then share the responses back.
That would be great.
Yeah. Okay. Once again, thank you everyone for joining. And thank you, Professor Masashi. This was a fantastic talk. I think you
thank you very much.
Really took us through decades of work as to how the fields have evolved and what is the latest state of the art here. So once again, thank you very much for taking the time out and for such a fantastic presentation.
Yeah, thank you very much. So bye-bye. Have a nice day.
Okay, thank you. And thank you everyone for joining. We will soon announce, our next speaker for the next month. So please stay tuned and please follow us on Twitter, LinkedIn, etc. to get to know all the updates. Okay. So thank you everyone and have a good day. Bye.